Okay, about type checking heterogeneous sequences in a simple embeddable type system.
Okay, thanks everyone for coming to listen to my talk. It's always a pleasure to talk about the things that you're interested in, especially to an agreeable and friendly audience. A quick overview of what we're going to talk about. I'll talk a little bit about the history of the project, and then rather than giving a lot of definitions and mathematical formulas, I want to go through a simple example, and I think that most of you can fill in the blanks and understand what it is that we're trying to do and what we're trying to represent. And then, as was explained in the paper, there are several very interesting corner cases and interesting challenges, technical challenges in the project, and I want to spend most of the time talking about those particular challenges. And there's some final thoughts. So a little bit of the history of the project. So when I started working on my PhD quite late in life, at the age of almost 50 years old, I presented a paper at the 2016 European Lisp conference about something completely disassociated from my PhD thesis, and then later on that involved into the thesis itself, and then I presented that in 2008. One of the comments from the committee was the thesis and the research was all about the type system in Common Lisp, and they asked, well, can't you generalize this to something more accessible to a general audience? And so what we're going to see today is some of my work on that, where I've extended this to the Scala, Clojure, Python, and then the original implementation is in Common Lisp. These are freely available for download from GitHub. So an example. What are regular type expressions, RTEs? I'll use the word RTE a lot without repeating potentially what it stands for. Basically, what we want to do is recognize patterns which have some type, recognize sequences which have some type of pattern in them, and where the patterns form something that looks like a regular language. So what is the pattern here? Here we have an integer followed by some numbers, which might be floats or doubles. The notation here is that F represents a float, and otherwise the floating point is a double. So integer, some floats, integer, some floats, etc. So I would like to define or declare some regular expression to declare that, to describe that type. A regular expression looking something like this: integer concatenated with double or float, and then that occurring one or more times, and the suite occurring maybe 0 or more times. So there are a couple of challenges in there. The highlighting doesn't look so nice. But one is, how do we represent this as a surface syntax in lots of different programming languages? And the second challenge is, well, how do I even represent logical combinations of types in a language-independent way? So some languages will let me represent intersection of types, but I don't have any programming language other than Common Lisp which lets me represent the complement of a type. So I would like to have any Boolean combination of types, as well as several other types, types of types. So how is pattern recognition of sequences normally done? Well, what you would want to do typically is convert the expression into some sort of finite automaton. And then, well, there's immediately a challenge. How do I do that in different programming languages? That needs to be done at what I'm going to call compile time. So even though that might be inefficient in some sense, there may be some complexities there that we're not so happy about. At least that computation happens at compile time rather than at runtime. And then at runtime, we want to use the finite automaton to match the sequence, to decide, is a given sequence a member of the language of that regular expression or the language of that finite automaton. So the way it basically works is, given a sequence, 13, 2.0, 6.0, and so on, we start in the initial state. We see that 13 is of type integer, so we move to state 1. We see that 2.0 is of type double, so we move to state 2. We get another double and then an integer, a string, integer, double, integer, and then again double. And we're at the end of the sequence, and we end up in a state which is marked with a double circle, so it's an accepting state. So we know that the sequence does match the expression. If anything else happens, for example, if we ever encounter a type or an element whose type is not listed on the transitions coming from the state that we are currently residing, or if we reach the end of the sequence and we're not in a final state, then we reject. We say the sequence is not an element of the language of that regular expression. One thing that you might notice or might not notice is that the decision criteria is linear in the length of the sequence. So regardless of the complexity of the expression might be arbitrarily hugely complicated syntactically, but to match a given sequence, we can do that in linear time by traversing the sequence exactly once. There's some problems that arise when you take an example that's not a trivial example. Suppose we're looking at this sequence, 2, 3, and then some floating point number. We see the first element is an integer, so we arrive in state 2, and then the next element is a 3, which is both an integer and a number. And integer is a subtype of number. So what do? So we might, for example, traverse the integer transition, and we find that the next character or the next element of the sequence is not of type string, so we backtrack. Now that's horrible because now the complexity of matching becomes exponential and no longer linear. So potentially that could work, we could get the right answer, but we really would like to avoid backtracking. So the solution that I propose is that we partition the types always into disjoint types. So 3 is an element of integer, but it's not an element of number and not integer. So then we can unambiguously, deterministically choose which transition to traverse, and we see that the sequence does match well, it is in the language of the finite automaton. That brings another challenge. Given a set of types, how do I partition the types? And what is a sufficient partition for the finite automaton to actually represent the language of the expression? And it wasn't at all clear to me at the beginning what is a sufficient partition. So here are the 4 challenges I would like to talk about in the remaining few minutes of the presentation. How do we represent these expressions in a way that can be translated into many different languages? How do we represent a type lattice in a language which doesn't already have a type lattice? So we can represent union, intersection, complements of types. How do we construct a finite automaton on this regular expression of types? Classical finite automaton theory talks a lot about languages on finite alphabets, but in this case, the set of objects in a programming language is an infinite alphabet. And then how do we make sure that those finite automaton are deterministic? So we have to do a sufficient type partitioning. So the first one turns out not to be so difficult. In the 4 languages that I've implemented in, we can represent in Scala with, I've defined a type hierarchy called, I forget the word in Scala used for this, ADT, algebraic data type, I think it's called, to be able to represent instances of this AST, algebraic syntax tree, or abstract syntax tree. So the internal nodes of the tree are the operators of the regular language, of the regular expression, and then the leaf levels are interfaces to the built-in types of the programming language, be that Python, Scala, whatever. And so here's the syntax in Scala. So we're using the infix operators which Scala provides and lets us override. In Python, it looks something like this. So we have constructors for the different objects. star, cat, etc. In Lisp, being homoiconic, we represent the abstract syntax tree just as an S expression in the language. There's no need for additional class definitions to be able to represent the expression tree. The second challenge then is how do we represent a type lattice in these languages? So I want to be able to reason about and or not of types, even if the language doesn't support them in a built-in way. We want to somehow wrap the type system or embed a new type system in the type system so that the regular type expressions can manipulate that embedded type system. We need to support a type lattice. It needs to be simple. So what is the simplest that it can be to represent the types of operations that we need to be able to do? As we'll see, there are two predicates that we have to implement in all the language. One is a membership predicate. Given an object is an element of a type, of a particular type, and that must be a Boolean. So it must answer true or false at runtime with no ambiguity. And then there's what I call a semi-Boolean predicate. So the subtype question is one type of subtype of another. Can be answered yes, no, or don't know. So whenever the system doesn't know, it must answer don't know. When it answers true, it means I've proved this is not a subtype. Or when it answers true, I've proved this is a subtype. When it answers false, I've proved that this is not a subtype. So again, there's a similar type of abstract syntax tree that you can use to represent types, with the internal nodes being the Boolean operators. As I said before, the membership predicate is always answerable, so we know that -42 is a member of the integer type. We know that 7 is a member of the type, which is the union of string and integer. And we know that 36 is a member of the type odd p, which is defined by some user-defined predicate. More interesting, and what makes the project quite interesting, is that given a set of types, we don't always know the subtype relations between them. So is integer a subtype of number? Yes. Is string a subtype of integer? No. Is satisfies odd p a subtype of integer? So you and I know that all odd numbers are integers, but given that this is a user-defined type, the type system doesn't know that, so it must answer don't know. There are many other reasons why the subtype question is unanswerable, in particularly because classes are loadable at runtime in some languages. So there may not be, A and B may not have a subtype relation now, but maybe later there is some type which inherits both of them, or the type lattice can change at runtime. Okay, so now how about how do we construct these these finite automata from regular expressions? So classical finite automata theory defines something called the Brzezowski derivative. I'll talk about that in a little bit, but we had to actually adapt that to our work because there are some interesting theoretical mismatches that will, again, make the problem interesting. We want to construct a finite automaton like this from this regular expression, from this regular type expression. And so the finite automaton is going to have transitions labeled by types, and the types are going to be Boolean combinations of the types that you see in the given regular expression. The Brzezowski derivative is defined sort of as a pattern matching. There are these recursive rules which, for example, for a R star, you find the derivative of R and then do something to that result. So there's these recursive rules where the derivative is called or is constructed on some subpart of the expression. And then there are the termination rules. So when we come to the empty set or to the language which just contains the empty sequence, then the derivative is the empty set. But the more interesting cases which did not match Brzezowski's original definition were the leaf level cases of the types. So when we descend the regular expression down to the leaf levels and we get types, we have to know, are we taking the derivative of some type with respect to some other type? We must know whether the types obey a subtype relation or whether the types are disjoint. With that definition, the regular expressions work correctly, except there's a problem. We don't always know the subtype relation. So how do we compute the Brzozowski derivative in a situation where we don't know what the subtype relation is? You get a very different result if the types are in a subtype relation or not. And how do we sufficiently partition types so that this expression is always evaluatable? So basically how we construct the finite automaton is we somehow extract the types we're interested in from the expression, integer, string, etc. We perform this partitioning, which I'm going to call MDTD, maximal disjoint type decomposition. And then for each of those types, we compute a derivative with respect to that type of the original expression. So if we partition into 10 types, we must compute this derivative 10 times, and then those types become the labels of the transitions. Let me show a more interesting one. When we have decomposed the types, when we have this type string and integer, we decompose them into string and even, string and even, string and not even, not string and even, not string and not even. So we have more or less 2 to the n different types in our partition. And then these types, if we follow the rules specified on the previous slide for the derivative definition, the derivative is calculatable. If we look at the state 3 here, we have 3 types that we have to consider. We partition that and we get potentially 8 different types. So we have like this 2 to the n relationship of the number of derivatives we must take at each step. But you notice string intersected with integer intersected with even is obviously empty. There's no object which is both string and integer. So many of the intersections will go away. They're called, I'm calling these unsatisfiable, a type which has no inhabited value. So if we can disjoin the types into a sufficient partitioning, then we can construct the finite automaton. But the question now is, how do we do the type decomposition in such a way that this expression is always computable by the recursive rules we saw, even in the case when the subtype relation is unknown? So imagine that we have a set of types that are partially overlapping. Some are subtypes of the others, some are disjoint. We want to find all of the non-empty intersections, and we want to somehow colorize the graph into all of the regions that don't overlap other regions. The way we do that is, well, let's take, rather than all of the 10 types here, 8 types here, let's just take 5 of them. So we start with the universe, which is called sigma in this case. We intersect with A1 and not A1. So those are clearly disjoint, and their union, again, is the universe. And then for the next step, we take the next type and intersect each of the leaves with both A2 and not A2. But what we see is that since A2 is a subtype of A1, then A1 intersect A2 is equal to A2. So this type name can simplify. But since A2 is a subtype of A1, then A1 intersect A1 not intersect A2 is empty. So some of the leaves get pruned very quickly in the process, so we avoid a super exponential explosion. The complexity is still exponential in the case if we have to actually compute exponentially many intersections, but many of the leaves get pruned very quickly. So we intersect with A2 not A2, A3 not A3, A4 not A4, A5 not A5, and in the end, because of the different disjoint relations and subtype relations, we get, I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 different types rather than 32 as you might expect in worst case. So these become the types we want to plug into the Brozovsky derivative. And so it turns out that, well, by construction, each of the types computed is either a subtype or disjoint type to all of the A1 through A5s, and we know which by construction. So even if the type predicate is not able to answer the question, is this type a subtype of some type or disjoint, we know by construction which one it is. Is it a subtype or is it disjoint? We know that all of the computed types are mutually disjoint by construction again, and we know that there is a partition of the original space, which is the universe. So these turn out to be the exact properties we need to compute the derivative. So how does that help in in assuring that the finite automaton is correct at runtime, that we do get the correct result? So rather than having integer and number as transitions, what we have is integer and number, integer and not number, not integer and number, not integer and not number, except that some of these go away if the subtype relation or disjoint relation is known. But if we look at int and odd, we don't know anything about the subtype or disjoint relation between those. So in that case, we do get potentially 4 transitions, integer and not odd, not integer and odd, even if the human being knows, for example, that not integer and odd is empty, for example. And that means that if we have a transition, for example, integer and not number, that transition can never be traversed. There's no object in the language which is both integer and simultaneously not a number. So this state 1 is useless. We don't have to actually generate it when we construct the state machine. And all of the states which 1 leads to can be omitted as well. However, in the case of a type such as string and odd, we know that that's unsatisfiable, but the machine doesn't. So we'll get transitions which exist in the state machine's construction at compile time, but at runtime, there's never going to be an object which satisfies that type, so the transitions will never get traversed. And in the case of int and odd, again, syntactically, it looks exactly the same as string and odd. However, this is actually a useful transition because whenever we get an odd integer, the transition would be applicable. So in some cases, we can't eliminate useless states. So minimizing these finite automata is then, well, it's impossible to completely minimize these. However, even in the case of useless transitions, the runtime check is still correct because whenever we get an object at runtime, we can test because the membership predicate always returns true or false. We can know if a particular object is a member of this type or a member of this type. Okay, so in conclusion, what we've done is we've come up with a way to efficiently pattern match or recognize patterns in what I call sequence of any, which this is the Scala syntax, and extended to several different programming languages. We've extended the Brozovsky derivative to accommodate types, and particularly types in a hierarchy where types may overlap or have subtype relations. We have a correct finite automata even in the case of an indeterminate subtype relation. Again, the code is available here. I invite anybody to take a look at that. Say just a quick word about critical feedback, that in a peer review process, researchers depend on other people to find problems with their work, not to be, nice citizens, but to speak up and say, hey, there's a problem here, there's a problem here. So I completely welcome feedback, even if it's critical feedback. And with that, I thank you, and I'd be happy to answer any of your questions.
So, are there any questions? So maybe, so.
You mentioned I've never heard of any language where you can intersect the negation of an integer. And have you heard of Elixir? Okay, Elixir is a language in the family of Erlang. So basically, it's more or less on types. It's as a very uh, simple type system like Prolog, but recently they have introduced a set-based type system where they also have intersection, union, and negation. So maybe some of your work can be used to give some sense, because it's a quite complicated type system, just to let you know. Okay.
Hey, so when you're doing these types, all of the types you have up here are like either what are built-in types in most languages, or user-defined types like odd, or user-defined predicates like odd. Can this system be extended to like composite types? So like if I had like a list of integers or something like that.
This simple embedded type system can encapsulate any type built into the language. So if the language has a composite type, it can be brought into the language trivially using this protocol. But some languages, such as Python or Clojure, don't have tuple types, for example. There's sequences, but not types of int or types of string, or sequences of int, sequences of string.
Kind of subsumed by sets and tuples, kind of subsumed the composite types we might want to bring into the language.
If you had a use case where that's not a sufficient generalization, I would like to know about it. But I didn't want anything in sets, the simple embedded type system, which was not supportable in all of the languages that I was trying to support. Yeah.
Hi, I wonder if there's been any research into what something like this might look like in a dependently typed setting. Or there's a concept of heterogeneous sequences, right? And I'm wondering if, what would happen if you said, well, I have a sequence that has types that satisfies this pattern, right? Where you could define your predicate at like the type level. Do you know of anything like that?
I know that Scala 3 has these dependent types, but I haven't not worked with them yet, so I don't know what the implications are of that. The membership predicate must be answerable. So in a dependent type system, given an object at runtime, can you know whether it's an element of a dependent type or not? With certainty? I don't know.
Oh, there it is. Hi, I just had kind of two comments. Following up on the discussion of type systems with negation, I thought I would just shout out, there is a pretty cool type system called cut out again, a language called ML from HKUST that has a whole kind of type system with proper negation. And also following on the dependently typed comment, there's also kind of an interesting line of work, I think, by Alan Jeffrey from a few years ago on linear temporal logic in a dependent type system, which I know sounds maybe a little unrelated, but does actually talk about sort of sequences and kind of non-trivial sequences of different types in a dependently typed setting. So I don't actually have a question. It was very interesting. I'd love to read more about this. I thought I'd just shout out two things that I like. I think the ML struct work, to my understanding, there's a variation on the notion of a constructor. So it's kind of not the same familiar thing you would think of as a constructor. Yeah. Yeah. So it's definitely a little bit more complex than that. Yeah.
So I think we have to stop the discussion and we can extend it in the coffee.